Unit 3 in AP Physics, Electricity and Magnetism is all about electric circuits. But to be able to understand electric circuits, we first need to understand some of the quantities that we'll be measuring and talking about conceptually in those electric circuits. The first of those quantities is current. Current is defined as the rate at which charge passes through a cross-section of an object. I like to think of this, for example, as if you were watching a highway from a bridge up above. You'd be looking at the rate at which cars are passing under the bridge. Since this definition is the rate at which something, we know that anytime we see that word rate, we're looking at a derivative, and this is a derivative with respect to time, like many of the derivatives we've seen in this course. So capital letter I is our symbol for current, and it is equal to dq dt, so the rate at which charge is passing through an area. If we look at the equation, we see that the units would be coulombs per second, and a coulomb per second is otherwise known as an ampere. Sometimes we shorten that to amps, and we use a capital letter A as the abbreviation there. If we want to have an electric current, then there must be a net flow of charges through a surface. So charges are moving around constantly. In a conductor, we have free electrons moving around every which way, and they're constantly moving. But if we have an electrical current moving through that conductor, then those charges are all moving in general in that same direction. And one last fact about current is that in a conductor, free electrons are creating a current. We know that electrons are the things that are able to move around. However, unfortunately, the direction of the current is defined as the direction that positive charges would flow. That comes from a few hundred years ago, before we knew what electrons were, and Benjamin Franklin randomly decided that we were going to go with positive charges moving rather than negative charges moving. So unfortunately, that's just something that you'll have to remember, that we're going the direction that positive charges would move if they could move, or opposite the direction negative charges move. Now, another thing that we can measure is something called current density, or the current per unit area. This is an equation that's not on your equation sheet, but you are expected to know it. You're expected to know of this idea of current density. And all it is taking that current and dividing it by the cross-sectional area of the wire. So most of our wires are kind of cylinders, and so the cross-sectional area would be a circle. But you may see some questions that deal with a wire that has like a square cross-section or something along those lines. The direction of current density is actually a vector, even though you don't see it in this equation here. And it's the same as the direction of the velocity of the moving charges if they're positive, and opposite their velocity if they're negative. So basically what this is saying is that the current density has the same direction as the current, even though current is not a vector and current density is. One last quantity that we'll discuss related to moving charges in conductors and in circuits is something called drift speed. So when a conductor doesn't have a current moving through it, those extra electrons, those free electrons, are sometimes called conduction electrons, are moving randomly. So constantly moving back and forth, maybe kind of not really bouncing off of things because they're not really touching other things, but maybe they're getting repelled from a nearby electron or attracted to a positive ion within the material. But when there is actually a current, those electrons are still going to move around randomly. They're not like moving in straight lines, but they tend to do what we say drift. So they may move around randomly, but they're slowly moving in one direction overall. You could think of this as like the difference between something's average speed and its average velocity. And so again, as we're thinking about the drift speed, we say speed in this case because we are not going to pay attention to direction, but really it should be like the magnitude of the drift velocity that we're focusing on. So that average velocity, looking at the displacement over time rather than how fast something is moving at a given second. If we have a wire where it has a length L, then that drift speed, or that average velocity, would be L divided by time. And we know also that current is defined as being dq dt, but if we have a constant current, as we will commonly deal with, we can change that derivative to just being delta q over delta t. And so if I were to solve my current equation for delta t, I would end up getting delta q over I, and then when I plug that in for delta t, I end up with length times current divided by delta q. And one more way that we can modify this, we can say that delta q is n times the charge on an electron, so n being the number of free electrons. And that's something that's actually a set value depending on the material that the wire is made out of. So you can see that we have that expression for drift velocity that says the length times the current divided by n times E. If I were to solve that previous equation for current, I would see that it's equal to n, which is the number of charge carriers, times E, which is a constant, times the drift velocity divided by the length of my wire. And then if I wanted to do current density, I could take that equation and divide it by the area, but now we have length times area, and length times cross-sectional area just gives us the volume. So you can see that I've written that there. One last thing, we can then say that the number of charge carriers per unit volume is a different variable. We'll call it capital N. And again, this would be something that would be set for the material. And so I may say this is a copper wire, and I can look up on the internet, or back in the day we used to look it up in tables, kind of reference tables. Okay, this is copper, so copper has this value of charge carriers per unit volume. And so then I can write the charge density as NE times the drift velocity, and the current as NE drift velocity times the area. Again, these are equations that are not on your equation sheet, but you're expected to have some knowledge of them. For the most part, really what you see on the AP test is knowing that current is directly dependent on drift velocity. Or things like that the current density is directly dependent on drift velocity. So the AP test is going to focus more on relationships between these quantities than it is on using this actual equation.